So we started to study BV quantization, and before turning to quantization itself, we need to discuss what is equivalence of BV systems. Okay, so what is the idea? The idea is that if we have a BV action, depending, say, on fields phi I, phi star I, which are fields that are the fields canonically conjugated in the anti-bracket, then what we can do, we can consider a new one. Let's say extended, which now depends on phi star and new variables w. Let me give an example which is closer to what we will need. For instance, some new variables c bar b, c bar star, and b star. Some new variables, and which equals to our s plus a new term c bar star b. This is what's called, let me better call it non-minimal, because this is the basic example, non-minimal. And the agreement is that because degree, it's just an example, it's not fully general, because degree of c bar is -1, and because degree of b is 0. If it is so, then c bar star has also degree 0, and this term has degree 0, right? And of course, the star indicates conjugation. So the bracket, the anti-bracket between c bar star is 1, and between b and b star is 1. In general, of course, there can be indices, but let me suppress it. There can be few variables c and b like this. So what is easy to check? It's easy to check, first of all, that the two sectors, the first sector of variables phi and phi star, and these variables c bar b and their conjugate antifields, they simply don't see each other. So of course it means that we immediately conclude that our S satisfies master equation in the extended non-minimal, let's say, non-minimal anti-bracket. Non-minimal. And of course, it is natural to say that this non-minimal action, non-minimal BV system, is equivalent to the initial one, right? Because what is the meaning of this system? The meaning is very simple. We have a variable. What are variables of degree 0? Variables of degree 0 are just b and bar c star. So it means that this term bar c star b depends on fields of degree 0. so it's a part of physical action. And equations of motion for B tell us that C bar star is 0, and equations of motion for C bar tell us that B is 0. Say all are gone, and variables C bar and B star, they are of degree -1, and they are just like anti-fields for B and bar C star. So they are usual. So in other words, variables B and bar C star, they are just auxiliary fields. But because we are working in BV formalism, we have, together with them, we have their conjugated anti-fields B star and C bar. So this action S non-minimal, this BV system based on S non-minimal at S are equivalent. Because the extra fields which we have are just auxiliary fields which are coming together with their conjugate antifields, though these antifields play completely passive role. So we should be able to always add such a trivial pairs. Of course, this was just an example. In particular, the extra fields present in the action, they had degree 0, so they're usual auxiliary fields, but you can equally well cook up an example where, for instance, let me try to do it another example, where we introduce new variables w of degree 0 and variable, for instance, c of degree 1. And then we can consider another non-minimal action, which reads like this. That's our initial action plus W star C. Of course, together with W and C, we have their conjugate antifields. What is the meaning? What does this term tell us? What is the meaning of such a term? Any idea? So the term which we just considered in the previous example, this one, was just a term with auxiliary fields. So C star bar and B are auxiliary fields. They are eliminated by their own equations of motion. They were in degree 0. Now we added different set of fields. Now we have just added a field W of degree 0 and field C of degree 1 together with their conjugate antifields. And we added a term like this. What is the meaning of such a term? If we see a term involving field of degree -1 and field of degree 0, what does such a term encode?
Maybe fix the gauge? No?
Well, it's indeed, it has to do with gauge symmetry, because C with a field in degree 1 is a ghost field. It corresponds to gauge parameters of some underlying gauge symmetry. So let me remind you what generic BV action look like. It looks like a 0. It looks like a 0 plus phi star I gauge generators and then ghosts. Would you agree that this structure is very similar? So we have anti-field, which means field of degree -1, then certain generator, let's say some matrix, and then field C alpha, which means that C alpha is a gauge parameter which generate gauge transformations of fields phi, which are conjugated to phi star. So what this example tells us is that there is a gauge symmetry which acts like this. So this term encodes a gauge symmetry, which acts like this. Delta W equals to epsilon, where epsilon is a parameter associated to C, right? So R is 1. So here the gauge transformation was delta phi I equals to Ri alpha epsilon alpha, right? And this is the same formula. So now the meaning of this kind of trivial variables is different, but still it is an equivalent extension of our system. The meaning is very simple. We introduce a new field W together with gauge transformation, which is just a shift gauge symmetry. So transformation of W is just epsilon, the gauge parameter. And this is reflected or encoded by such a term in the mass direction. Of course, S does not depend on these new fields W, otherwise there can be some mixing. But we just did a trivial extension. We added a new sector which doesn't see the initial S. And this is again kind of trivial variables which are not related to auxiliary fields in their standard meaning. They are pure gauge fields, right? So this W is a field for which gauge symmetry is just a shift transformation. But in BV formalism, where BV master action takes care not only of Lagrangian but also of gauge symmetries, reducibility relations between gauge symmetries, etc., such a term W star C encodes this gauge transformation, which we discussed. Very good. Of course, one can cook up different examples of the same sort, taking different Gauss degrees, but the idea is always the same, that you add a new sector, which is kind of trivial. Why it is trivial? Because here the physical meaning is very simple. We can just gauge fix W to be 0. This would eliminate gauge parameter because we don't have gauge symmetry any longer. And of course, all the anti-fields and anti-fields for Gauss should be also gone because we eliminated this symmetry. In this case, we have fields in degree 0, but they eliminated by their own equations of motion. And also, together with this, we need to throw away their conjugate antifields. In a similar way, one can consider such a trivial terms of different degrees. You can consider it as an exercise to find an example, for instance, of a term related to gauge for gauge symmetries. But what is important is, for instance, that such BV systems should be considered physically equivalent. And in particular, it's not difficult to make sure that cohomology doesn't change under such a trivial extension. For instance, let's consider the BV differential associated to this action. So let's go to the next page. So let's say we have S non-minimal. It's a small s, which is a bracket with S non-minimal. And which is initial S. We keep it implicit. We don't care what is inside, but we know that it is nilpotent and that it doesn't touch our new variables. And then we have extra terms, which are what? Which are C d over d W, right? Plus, so we have W star C. So there are two terms in the Hamiltonian vector field with such a Hamiltonian. So one is one I wrote, C d over dW, and another one is going to be W star DODC star, right? Is the sign correct? I think it is correct, yes. So we have the following differential. And again, this term looks familiar to us, right? Because it again looks like the Ram differential or Koszul differential. And we know the standard argument that if you compute cohomology of this term, these are going to be, so cohomology of this term CD over dW plus W star DODC star in the space of, say, functions, polynomials in CW, C star, W star, this is going to be what?
Constants?
Yes, exactly. So this is going to be C, right? If we have complex, if you consider complex valued functions, this is going to be C in degree 0, and in higher degrees, of course, it's empty. In higher, yeah, well, the constants in degree 0, and all other Gauss degrees, the cohomology is empty. Yes, but because we also have additional fields which were initially present in our system, now this term would give us just functions of the initial variables. So it means that somehow presence of such a term just eliminates this new variable CW, W star, C star, and we are back to our initial system. So what is important is that cohomology of S non-minimal in whatever reasonable space is isomorphic to cohomology of the initial S. So indeed, we know that physical quantities are described by cohomology, and we know that cohomology is unchanged, so it gives us additional argument why such system should be considered equivalent. But let us try to give a more general setup. And the term which is used for this is called, the term is generalized auxiliary fields. Why generalized? Because first of all, these are like auxiliary fields in BV formalism. And so they are auxiliary fields for the master action in a certain sense, but they correspond not only to auxiliary fields of the underlying classical action, but also they correspond to pure gauge variables or trivial reducibility relations, some things like this. For instance, like in this example, which we just had, this in this setup, this trivial part corresponds to pure gauge variable W, for which the gauge transformation is just a shift. And again, this situation should be covered by this concept of generalized auxiliary fields. But let us try to give definition. So suppose that our action depends, that we can do a field definition if necessary, and we can assume that our BV action depends on variables phi star, W, and W star, and star is usually denote antifields. Of course, it's defines for us BV system. And suppose that the equation, the Euler-Lagrange equation of the master action, not of classical action, this is important, W star, let's say alpha, this is Euler-Lagrange equation, it can be algebraically solved, so which means it is just equivalent. But what is important, we need also to set this to 0. So if we impose Euler-Lagrange equation associated to W star, and additional equation which just sets W star to 0, what we get is that it can be solved with respect to W. So this equation is these equations equivalent to W equal to some, let's say, big W of phi, and phi star. So it's just like in the definition of auxiliary fields. That's why these are, sorry, these are auxiliary fields for the master action. But the subtlety is that they come into pairs. So we ask W star to be W star to be auxiliary in the following sense, that Euler-Lagrange equation associated to W star together with W star equals 0 is solved with respect to W. So they are like eliminated. And then it turns out that the reduced action, BV action, reduced, which is S of phi star, capital W of phi star, and 0. So we restrict our initial BV action to this surface, to Euler-Lagrange equation for W star, and we set W star to 0. This is in U like reduced BV system. We say that this BV system is obtained by elimination of generalized auxiliary fields W star. So again, if this equation can be solved with respect to W algebraically, we say that W and W star are generalized auxiliary fields. Generalized auxiliary fields can be eliminated, which means we can set them to their values. We still have an anti-bracket in the sector of phi and phi star. So we have phi and we have phi star. They are canonically conjugated. Let's say I j. So here we get delta ij, and it, because implicitly we are working with field theory. Here
there's a question in chat.
Could you please read it, because I don't want to switch.
There is a question whether the star in the Euler-Lagrange equation is not needed above W. Should it be there?
Sorry, just one moment. Let me. Oh, yeah. You're right. Yeah. You're of course right. Yeah, that's sorry for the. Yeah, like this. Indeed. Now it is correct. Yeah, I confused notations. Yes, right. So indeed, it's right. It's easier to remember like this. So W and W star are auxiliary fields if equations for W at W star equals 0 algebraically solved with respect to W. Then indeed we cover usual auxiliary fields easily. Yes, indeed, it was I confused. Good, thank you for the correction. Yes, so once we have it, we can eliminate these fields and get a reduced system which contains only fields phi and phi star. They are canonically conjugated again, and there is a new reduced action. BV action. And in fact, one can check, and this is an exercise, that this reduced action again satisfies master equation with respect to reduced bracket. Reduced means where W is not present any longer, just for phi and phi star. This fact has a simple geometrical meaning. If we, for instance, let me sketch a proof in the case where our space is finite dimensional. So we consider the surface ds over d w alpha 0, w star alpha 0. And then we have a form. Initially, we have our symplectic form was d phi star, like this, right? Plus dw alpha, dw star alpha. So this was our symplectic form before the reduction. And now we pull it back to this surface, right? So we have this surface, let's say sigma in our field antifield space. So of course we use phi and phi star, or more precisely their pullbacks to the surface sigma as coordinates. And it's immediately clear, because w star equals 0 is one of this is one of the equations, that this term disappear and this remains unchanged in this coordinate system. So omega reduced, omega reduced is just d phi I, d phi star I, right? In these coordinates, phi and phi star, which strictly speaking, I should have called them differently, but because these are coordinates on sigma, not on M, right? But they are just pullbacks of phi and phi star, so it's quite economical to use the same notation. So we are again dealing with all the symplectic manifold, right? With such a symplectic form. Okay, and what else we know? We know that our master equation can be written like this. We can introduce small s. We can introduce Hamiltonian vector field S, which is BRST differential, which is a Hamiltonian vector field with Hamiltonian our master action. And then we know that this S is tangent to sigma, right? Because S acting on W star alpha is nothing but ds over dw alpha, right? Just because if we take anti-bracket with W star, it's the same as taking a derivative like this. And so we get another equation. So our surface is determined by these two constraints. So what we need to check to make sure that S is tangent, that S acting on the constraint is again proportional to constraint. You see, we act with S on this constraint W star, and we get another constraint. If we act on another constraint, we get 0, because it's already it's like S W star alpha, and this is 0 identically because S is important. So S is tangent. Then we know that master equation can be written as omega symplectic structure evaluated on SS, right? It's another way to write up to coefficient. It's just this, right? Just putting index down and up. And this, so, but now look at omega red, S red, S red. Because BRST differential is tangent, when we evaluate this expression at the surface, we just, it's exactly the same as evaluating this expression at the point of the surface when we look at it as a on our big space on M, right? So this is 0, and hence this is also 0. So it's a simple geometrical proof of the master equation satisfied by reduced master action. What is more interesting is that one can prove under some technical assumptions that elimination of generalized auxiliary fields is an isomorphism of cohomology. So indeed, this procedure can be thought of as equivalence transformation for BV systems. So the statement reads like this. So cohomology, let's do it in a finite dimensional setting, but in fact it remains true in local field theory as well. So if we have cohomology of S in C infinity M, this is isomorphic to cohomology of S red in C infinity sigma. So what is a sketch? Again, I only give a sketch of the proof, and more detailed proof remains as an exercise. And let us restrict to finite dimensional, to the situation where M is finite dimensional. So assume, otherwise it's a bit more subtle. Assume M finite dimensional. So what we do, we introduce new coordinate system. New coordinate system, which is our initial functions phi star, then W star alpha, and S W star alpha. Now our S reads like this. It's and this I denote by V alpha. In this coordinate system, our differential can be written like this: V alpha d over d W star alpha plus S I phi star W star V d over d phi I. This is first step. So what is important is that we get such a term here, which in fact we already saw. Do you remember when we discussed a very simple example of this non-minimal extension, which is precisely a particular example of elimination of auxiliary fields? The structure of our non-minimal differential was exactly like this here, right? So it was a piece like initial and this, let's say, contractible piece, which looked like the Ramo-Koszul differential. Now the situation is more subtle. So we, by changing variables, we found that we can identify such a contractible piece, which is already a good sign, which suggests that these variables v and w, they disappear from cogomology and give us what we want. But in contrast to the naive example which we had, now this term, the coefficients of this vector field in this coordinate system, still depends on w star and v. So if we could eliminate this dependence on w star and v, we would get back to precisely the initial setup, and the standard argument would be that we just, so these functions of phi star would play a role of constants, and we evaluate this cogomology, and there are standard arguments telling us that cogomology of S then is isomorphic just to cogomology of this piece. And this is a bit of a technical trick, so let me leave it as an exercise. Prove that there are coordinate functions, let me call it, let's say var phi, like this, which complete, so this is a full coordinate system where S equals to no, I was not very careful. Here we also have piece with I forgot to write, of course, SI. It was the same d over d phi star I. I forgot one piece here. Sorry. And so what we can check? We can check that we can actually modify coordinates phi and phi star. I call all of them all together var phi, such that the differential start to have the structure like this. It's SA of phi only, d over d phi a. And then the statement is obvious that because these two pieces of the differential do not see each other, we can conclude that variables v and w star disappear from cogomology. And this SA is precisely this piece of the differential, is the restriction of S to the surface V equals 0, W star equals 0. So it's precisely the reduced differential. So we prove, if we succeed in showing that we can pick coordinates phi in such a way that differential takes this form, then we are done. Of course, we don't take global geometry into account. All these are local considerations, local in the sense of a coordinate neighborhood. Okay, good. And the hint is look for phi in the form of formal series in W and V. Let's say some initial, which is just 5 star plus V on something plus W on something. And then you can do recursive proof showing the existence of such a coordinate. That's an exercise. Okay. So this is a very important concept because in gauge theories, the concept of generalized auxiliary fields, because in the reality of gauge theories, we often meet formulations, different equivalent formulations of the same system, and sometimes it's even not so easy to understand that we are speaking about one and the same system, just formulated differently. In case of usual field theory, this is kind of, if you don't have gauge symmetries, the problem still exists because we can always introduce auxiliary fields. For instance, we can work with in terms of first order action or second order action. These two actions are related by elimination of auxiliary fields, right? And still it's a bit of work to check that one is equivalent to another. But in the case of gauge theory, the situation is even worse. On top of auxiliary fields, you can have pure gauge degrees of freedom. You can have dependent gauge generators and all this mess. But it turns out that in BV formalism, all these relations are captured by this concept of generalized auxiliary fields. They, at the same time, they describe usual auxiliary fields, pure gauge degrees of freedom, and more general situations. And still, elimination of these generalized auxiliary fields is a good equivalence relation. Okay, and now we get to more to quantum level. We will stick to just formal considerations, formal path integral. I'm not going to discuss any subtleties related to regularization, renormalization, etc. So it's going to be just a formal path integral. And so the question which we are going to address now is how can we formulate path integral in BV with the help of BV. Path integral with the help of BV. For instance, suppose that our S0 classical action is non-degenerate, so no gauge symmetries. Then, of course, we can do usual path integral. We can say that, for instance, average of an observable f is just an integral d phi f of phi and the integration goes, and we just forget about anti-fields, right? Or more geometrically, we can think of integrating this object over the surface. Think of it as an integration of this object over the surface phi star equals 0. And here we have some measure. For the moment, we don't discuss the subtleties of measure. Okay, so if we are dealing with theory without gauge freedom, then of course it's a toy model. It even looks stupid. Then we can say that we can do we can do path integral over submanifold where all antifields are set to 0. And because our action is not degenerate, this integral is well defined. So F is observable. Of course, we say nothing new. You can immediately ask me, why do we then need antifields because anyway we set them to 0 afterwards. But the situation becomes more interesting in the case of gauge theory. In the case of gauge theory, our S SBV is something like S naught plus phi star I alpha C alpha plus more. And we know that the rank of d phi should be, so the degeneracy of our B action. It's not a good notation. I need to let me use it here. D Z A D Z star. So the dimension over 2, right? Which is by definition dimension of my field antifield space over 2. So it's maximal, and our master action is proper when this rank is maximal. So this means that if we integrate our master action over the submanifold of dimension half of the total dimension, then we have a chance to get a well-defined integral. Because the problem is that if the object which we integrate is degenerate, which means it has gauge symmetries, then the path integral is not well defined, because we integrate along the direction on which the integrand doesn't depend, and we apparently get infinity. And this, so integrate in naive terms, we integrate over gauge orbits, but gauge orbits are infinite, and it gives us an undefined expressions. So the idea of BV quantization is that we integrate BV action over a surface, gauge fixing, it's called gauge fixing surface, which is precisely of dimension 1/2, but which in general is more tricky than just a surface where where we set to 0 our antifields. And the recipe is that we need to integrate over the surface, which is determined by the following equation: phi star I equals to d psi over d phi I, where psi is a function of phi, of fields, not of antifields, and its Gauss degree. In order for this to work, we need Gauss degree of psi to be -1. And this is called gauge fixing fermion. Traditionally. So you see, it's a generalization of what we had of the naive situation of a non-degenerate system. In that case, we in that case, this psi, this gauge fixing fermion, is just 0. And we get phi star equals 0. But in a more general setup, we could, what does it want to do? How to get rid of this? Sorry. Yeah, sorry, it's not my my tablet, and I'm not very. I'm afraid if I click here, something is going to happen. Yes, exactly. Sorry. I hope it's done. Yeah, very good. It was not so bad. Okay, so the general recipe is to consider a surface in our space of fields and anti-fields, which is determined by the following equation. That anti-fields are gradients of components of a gradient of a function, of a scalar function, and this function is called gauge fixing fermion. In geometry, such submanifolds of symplectic manifold are known as Lagrangian. It's a particular example of what's called Lagrangian submanifold. What is the definition of Lagrangian submanifold? It's a submanifold of maximal dimension. It's half of the total dimension, such that the symplectic form restricts to 0. This is more or less obvious here, right? We get rid of all anti-fields, we stay with just fields, and the pullback of our symplectic form to this surface is obviously 0. So the recipe is to integrate the BV action in the path integral, not over the entire space, but over the Lagrangian submanifold. And because if our master action is proper, it means that somehow the rank of its Hessian matrix, this rank, is maximal, so it's half dimension. If we choose this Lagrangian submanifold properly, we get a non-degenerate system with a well-defined path integral. So of course, we need to pick a right psi for this to work, but at least in principle, it should work. And let's see how it works. For the moment, we don't go into details. We just assume that there is some generic BV action and some surface, which some Lagrangian surface, such that the restriction is non-degenerate and the Lagrangian is well defined. Then the crucial fact is as follows. So first of all, before fact, we need to introduce one object. So the name of the object is delta operator. It's traditionally called like this. So what it is the second order differential operator acting on functions on fields and anti-fields, and by definition it is like this: -1 to power I, Grassmann degree of phi I, d over d phi I, d over derivatives are right derivatives. Here it's important, I star I. So such a strange operator which look like Laplacian. And here I use the shorthand notations that this thing is Grassmann degree of phi I. Otherwise it's too heavy to write. -1. So we need a special sign factor. So what are properties of this delta operator? So first of all, of course, its Gauss degree and parity is 1, right? Because it takes derivative with respect to field and its conjugate anti-field. But conjugate anti-field, there is a shift by 1, so we get this Gauss degree 1. The second property is that actually it's important. This is quite simple to check, because if you go twice, you will see second derivative in fields and second derivative with anti-fields, but they have opposite Grassmann parities. So one expression is symmetric, another expression is anti-symmetric, so the contraction is 0 by symmetry. If it's not obvious to you, please check. So exercise check properties. And the less trivial property is as follows. So if we go with delta on a product of two functions, because it's second order, we don't have Leibniz rule, but what is interesting is the deviation from Leibniz rule. So delta f times g plus minus 1 to power f, Grassmann degree of f delta g, but then there is one more term, which is precisely the BV bracket between f and g. So an exercise is to check all these properties. Well, the first one is completely trivial. So you see this delta operator is a very interesting object. It also knows the BV bracket, because you can define BV bracket as a deviation of the Leibniz rule for delta. So because delta is second order, it doesn't satisfy Leibniz rule, so which means that in addition to this term and this term, there is an extra term. And this is precisely this discrepancy, this deviation, which is the anti-bracket. So anti-bracket is determined by delta. So somehow it's a more fundamental object. Unfortunately, there is one issue which I have to warn you, that delta is usually ill-defined. Well, it can be and it must be defined, but in a naive way, it's ill-defined for local functionals in field theory. So our considerations now are a little bit formal. Okay, so we introduce this important object, and then we have the statement which I promised. So if we have the following, consider the following integral over phi of a function I of fields and anti-fields, but where anti-fields are set to their values on the surface. So consider the following integral, and it doesn't depend on small variations of psi, provided so if we have a function of fields and anti-fields that satisfy this equation, then if we integrate it over a surface determined by psi, that the integral does not depend on psi. Well, of course, it depends in general, but if we vary psi slightly, like infinitesimal variation of psi, we deform our surface a little bit, then the integral is unchanged. And this smells very good. It smells like gauge independence, right? So if this I is something describing our theory, then such an object, such an integral, is well defined in the sense that it doesn't depend on the choice of gauge, because as you can anticipate, this psi encodes the choice of gauge. We need to gauge fix in order to go to quantum theory, right? Otherwise we can't evaluate path integral. But what we want, what remains of a gauge invariance at quantum level, is the independence of our physical quantities on the choice of gauge, because gauge is like a technical gauge condition is like a technical step which is needed to compute something, but nothing should depend on the choice of gauge provided the choice is good. So at least if we vary our gauge condition a little bit, then physical quantities should be unchanged under such a variation. And that's exactly what this statement is for. And another thing, it's modular boundary terms, strictly speaking, but we assume that boundary terms that we assume that they don't contribute. Boundary terms in the path integral. Okay, the proof is surprisingly simple. So let's just consider the variation. So let's see what happens. So we have variation of our integral is nothing but integral d phi I of phi and d delta psi. If delta psi denotes a small variation of our psi, d phi. So how can we represent it? What we can do, oh, sorry, this is, it's not correct what I'm writing. It's not right. So the variation should look like this. It's di over d phi star evaluated at phi star equals d psi. And then we have d delta psi over d phi I, right? Yeah, like this. And psi is a function, let me remind you that psi is a function of phi only, doesn't depend on phi star. So this is our variation. Then we do integration by parts. So we move this derivative to here, assuming that boundary term vanish. But what about sign factor? Yeah, one has to be careful with the sign. But you see the idea. We are going to get, so we do it by parts. And we are going to get delta acting on I, which is 0 by assumption, plus additional term which also vanish. But what worries me now is how do I get a right sign factor? Oh, right, yeah, one has to do it carefully. One has to do it carefully because, yeah, if I write it like this, then this derivative should be like this. Then this expression, the parity of this expression is opposite to that of phi I. So I don't get additional sign, but then I get a sign by transforming this derivative into a right derivative into a left derivative. For this, I get a sign factor, precisely the one I need. So what it gives to me, it gives to me integral d phi minus 1 to power I. This I get by transferring derivative to transforming derivative from left to right. And or maybe with plus, but it doesn't matter. Overall sign is not important. It's here we get d over d phi I, d over d phi star I of I. Yeah, that's what we get in here, just delta psi, right? And this produces me two terms. So one term is just one term is just delta acting on I, but another term is when this derivative will hit the deep psi in the argument, but this vanish on degree reasoning. So anyway, sorry, because there is something symmetric and anti-symmetric. So all in all, it is proportional to delta I, which is 0. It's an integral of delta I times something. So we have checked that our integral, like this, that it doesn't depend on the choice of psi, or at least if it is a small variation of psi. Of course, if we change psi substantially, we can get something else because it's like a different equivalence class. And the meaning of this is gauge independence. Okay, so now we know how to form integrals which do not depend on the choice of gauge. But what we want to integrate, we want to integrate the exponential of the action, right? So we take I to be exponential of an action. Now I use notation W because it's like a quantum action in the sense that it might contain H bar corrections. And so in order for such an integral, if we now form an integral, for instance, like this, d phi ei over H bar W, and this we evaluate at phi star equal to d psi. In order for this thing not to depend on psi, we need this condition to be satisfied. It's not difficult to see what it means because, so let me do it explicitly. So we have d minus 2 power I, d over d phi I, star I, exponential. So So here we get dw over d phi star I, again exponential. And then we get two terms, right? So the one is going to be just delta w, exponential times exponential. And the second one is when this d phi would hit exponential. So this is going to look like it's important to put derivatives right. And then dw over d phi I, and again exponential. Okay. And now we see that this term is precisely 1/2 of the classical master equation of an anti-bracket of w with w, right? Because this sign is used to change this left derivative into right derivative. And in the master equation, the bracket contains two equal terms, and this is one of them. That's why we get half. So if we continue, what we get is oh, sorry, and I forgot right coefficients. So here I get I over h bar. And here I also get r squared. Okay, so all in all, this gives me the following condition. This gives me, and it's called quantum BV master equation. So you see, it is like it's like a correction of a classical. So if we set h bar to 0, we get just classical equation. In fact, this can be made more precise. If we assume that w is an expansion in h bar, which starts with classical PV action, S plus IH bar W1 plus IH bar squared over 2W2, etc. Then what we get, then this equation implies, of course, that at zeroth order to H bar, in H bar we get S equals 0, right? And the next step we get S W1 equals 0. And one more is something like W1, right? Equals to so what do we get at order 2 in H bar? We get indeed of W1 plus S W2 equal to H delta W1, right? No, but without H, we already took into account. Yeah, that's what we get. We get this, and we can write higher. But what is important is that for H bar at 0th order in H bar, we have something satisfying classical master equation, and then we have like equations on quantum corrections to the classical action. And that is why we identify S as a classical BV action. Okay, good. But how am I doing with respect to time? Not very good. Time is running. But what we really need, so we now see what are conditions satisfied, which should be satisfied by the integrand of the path integral. So we see the equation on the quantum BV action. It's a deformation of classical BV master equation. But what we really need is not just a gauge independence of a path integral of the action, but a gauge independence of quantum average of observables, right? What we really want, we want to evaluate something like, for instance, something like this, which is going to be, now we write it like this, H bar W F. And this we integrate over the Lagrangian surface. So phi star equals to d phi. So what we really want is that this integral is gauge independent. This, we apply the same logic. We know that for such an integral to be independent, the expression under the integrand must be in the kernel of delta operator. So what we need to make sure that our quantum average doesn't depend on the gauge condition which we use when we evaluate it, we need to impose the following conditions: that delta acting on F times I over H bar W is 0, right? So let's compute. It's simple. So we get delta F plus, there are going to be 3 terms, right? The anti-bracket, like this. Oh, sorry, I forgot here to write. So it's delta F times exponential. Then we have anti-bracket, like this. And the last term, when delta hits exponential, but we assume that W satisfies master equation, so it's going to vanish. But let me anyway write it. Yeah, so we get these 3 terms. I continue the equality, and this must be 0, right? This is 0 on account of quantum master equation, because this is precisely quantum master equation, that exponential of W is annihilated by delta. So we get only these first 2 terms. So what we get is delta F plus H bar F is W, and all this is multiplied by here. I don't like sign factor. must be here, -1 power f, right? And this we're going to rewrite as follows, that it is delta f in fact, if we exchange the arguments of the anti-bracket, we get exactly so if f is bosonic, then we get nothing, and if f is fermionic, we precisely compensate. Yes, that's right. Okay, so we get a condition. This is non-vanishing, so f should satisfy this, and for this we introduce so we write this condition as we introduce differential SW, which is bracket with W plus minus IH bar delta. And the condition we get is that SWF is 0. So this is the condition that our path integral of exponential of the action with f is gauge independent. And this differential SW is called quantum BRST differential. And it's a simple exercise to make sure that SW squares to 0. So it's indeed differential. And one can speak about quantum BRST cogomology, but again, let me warn you that this delta operator in realistic field theory is quite an ill-defined object. So one should think of it rather formally or assume that some kind of regularization has been done. Okay, and then second part of the exercise is to make sure that if the trivial observables, so the ones which are in the image of SW, so we know that observables must be in the kernel, quantum observables must be in the kernel of SW for them to give a well-defined quantum average. But those which are in the image result give their average is 0. So this is also easy to check. So if we have integral d phi, and here we have SWG multiplied by exponential of our action, and all this evaluated at phi star equal to d psi, then this is 0. This is a simple exercise. Okay, very good. So we know now, at least formally, we know what is how to formulate path integral in BV formalism, how to impose gauge conditions in BV formalism, and what are observables at the quantum level. And all this is at least formally consistent. Good. Then let's try to see in more details what it looks like in terms of a gauge theory in question, because these are very, very formal considerations. So let's pick an action, the standard example for us. Let's take S to be some classical action of phi, and the simplest situation where we only have independent gauge generators, so-called irreducible gauge theory. So here we have phi star I, Ri alpha, C alpha, plus perhaps terms of higher resolution degree, but they are not important to us now. And of course, we assume that master equation is satisfied. So what we want to do in this BV formalism is to impose some kind of gauge conditions. These are not most general, but what we want is to impose some kind of gauge conditions like this, right? We use the same letter alpha, same index alpha to denote conditions, because there should be as many conditions as we have gauge parameters, right? If our gauge transformations are independent. So these are the gauge conditions we want to impose, but let's see how conditions of this sort naturally emerge in BV approach. So what we are trying to do, we are trying to find psi, depending on our fields, which would impose such a condition. But we immediately fail. Why? Because our fields now, so our fields phi, these are just fields in degree 0 var phi and ghosts. We don't have more variables. So these have degree 0, these have degree 1. So we can't find a function of fields which has degree -1. So somehow it doesn't want to work. But in fact, the way out is very simple, and it exactly has to do with this equivalence we discussed in the very beginning. So the idea is to equivalently extend. So go from S to S non-minimal, which depends on top of fields which we already had, which depends on variables of non-minimal sector, which are C bar alpha there and B alpha. These are of degree -1, and these are of degree 0. And of course, their conjugate antifields, which is C bar star alpha in degree 0 and B star alpha of degree -1. Yes. And our non-minimal action is just our initial action plus C bar star alpha B alpha. And this is precisely the example we had in the beginning of the lecture. These are generalized auxiliary fields. We can always add them, extend our field antifield space, and this doesn't change our physical system. In this case, this C bar star alpha and B are just usual auxiliary fields equations. They are killed by equations of motion. But now, at our disposal, we have variables of degree -1, which are C bar alpha. They have degree -1, and they are not antifields in our notations. So we can cook up something of degree -1. So let's pick psi. In order for it to have degree -1, it must be linear in C bar alpha times, and here precisely we get a room for a gauge condition, chi alpha of phi. Of course, one can consider something much more general, but let's for the moment stick to this one. And then let's evaluate explicitly our gauge fixed action. So our S gauge fixed, which is going to be just S non-minimal, where we set all fields or all anti-fields to be just components of a gradient of this psi. So, but you see, this psi depends only on C bar and on phi. So something non-trivial happens with C bar star and with phi star. So let's evaluate. So our gauge fixed action is, I don't have much place, so let me continue this equality here. So our S gauge fixed is nothing happens with fields, so the first term is unchanged. Then we have this term phi star I, which should be replaced with phi star should be replaced with a gradient of psi with d psi over d phi I, right? So it gives me C bar alpha d chi alpha over d phi I, and this, and then the remaining terms are I alpha C alpha, right? So this is the first term. And then another contribution could come from the non-minimal, from this one, right, where we have C bar. So C bar alpha, C bar star alpha is d psi over dc bar. So what we get here is just B alpha chi alpha. And if these extra dots, in principle, they can be phasor terms, but in the simplest situation, if we don't have quadratic in phi, we have nothing, right? Because here we either have terms phi star times something, or C star times something. Phi star, if this one is not present, this is 0, so that's it. So this is our gauge fixed action. And I hope you recognize what is the meaning of this action. It's very simple, because our B alpha are bosonic variables, so they come multiplied by gauge conditions chi alpha. So if we integrate over B, we get precisely delta function of chi, but we have an additional term which contains C bar and C times the following like gauge variation of the gauge condition, and this is precisely the term which I'm sure you saw it in Fadeev-Popov prescription for quantization. This is precisely this ghost term with ghost C and C bar, which computes a right determinant so that the integral does not depend on the choice of chi, right? Because if I choose different chi, even if it describes the same gauge condition, in principle, if I need to compensate this change by a certain measure contribution so that the integral is unchanged, and this ghost C bar and C, they precisely take care of this. This is standard story from Fadeev-Popov action. But now we recovered it from a very general perspective, and by construction, we know that the action should be, we don't need to prove gauge invariance. We already proved it in the very general terms. So we know that the integral does not depend on a small variation of the gauge condition. So what we arrived at is a version of Fadeev-Popov action. So somehow we derive it from more general BV prescription. But of course, the advantage of BV is that it's applicable to a much more general situations. For instance, if there were terms like this, which means that our algebra is open, we would know what to write, right, in the action, because we just apply the systematic procedure. Okay, good. I'm afraid I have to stop already. I'm late for couple of minutes already. So thank you very much. And we, okay, regarding plans. So I plan to give a lecture in 2 days on Friday in our standard time slot. And I think we need at least one more so that I cover the material I wanted. Still not everything I wanted, but some minimal. So I suggest to have additional lecture also next week on Wednesday, and then perhaps stop, at least officially stop. So this is my proposal, but anyway, I will remind you in our joint Telegram chat. So thank you and see you next time.